So this lab is consolidation test lab, lab number 9. And here we will be studying consolidation properties of clay soils. So here is on the top an example of a filled situation where we may have a layer of clay uh, sandwiched between sand below. It could also be bedrock or some other soil type. And there is sand above, there is a groundwater table, and then we are applying some load. Let's say we are going to construct a building here, or build an embankment, or we are going to put a fill, so a road could be constructed. And for any of these reasons, there could be an additional load applied, which we are going to call delta sigma. So here is a representation of what happens on the right side. So when we apply the load delta sigma, the sand has high enough permeability where the water squeezes out in reaction and the sand settles immediately. But in clays, the permeability of the soil is so small that it takes a while for the water to come out. So as soon as we apply the load, or in this case, weight W, which puts some stress on top of the soil, this clay layer can be looked at as a spring and water in a chamber with a very small opening. So as soon as we apply the load is taken by the water because the water cannot escape that quickly. And then with time, the water slowly drains out, and in reaction to the applied load, the soil settles. So if the original thickness of the soil layer was H0, under the load, it's going to settle to some new height, and the settlement is going to be delta H. Okay, so delta H is the settlement in reaction to the applied load W, or equivalent stress delta sigma. And we want to figure out how much that settlement is going to be. And one can imagine the higher the load, the settlement is going to be increasing some. And the second thing we want to find out is how long it's going to take. So we want to find out how much is the settlement and how long will it take for the soil to settle. Okay, so for the first part we need 3 parameters: compression index, recompression index, and pre-consolidation stress. And for how long, we are going to determine a soil parameter called coefficient of consolidation. So imagine that we drill a hole in this ground and retrieved a small soil Shelby tube or a soil sampler and brought it to the lab. And you will see in the lab video how a sample could be extracted. So we take a small sample which is in relatively undisturbed state, and that goes here. Okay, so this is an apparatus where we have a ring that restricts the horizontal expansion of the soil sample. So under the applied load from the top, okay, this force P, so the load P divided by the cross-sectional area of the soil sample will give us the stress that we apply to the sample. And because of this ring on either side of the sample, or the ring holds the sample cannot expand in a horizontal direction. So the only way it can compress is in the vertical direction. And that's why it is called as one-dimensional consolidation test. Okay, which represents this schematic on the top, where we are applying some vertical stress uniformly across a soil layer that's uniform and extend infinitely on both sides. And in this case also the soil is going to settle only in the vertical direction. So the idea here is to change sigma, um, the applied stress, and keep track of the settlement. And for that we use a transducer, which is a displacement transducer. So we know the original height of the specimen, the soil specimen, and with the application on each incremental stress, we find out how much is the change in the specimen height and use that information to find the soil parameters that we are going to find. So we can imagine, so the way we are going to do this stress is that sigma is going to be 15 kPa let me get the numbers. So the load sequence we are going to get is 15 kPa, 30, 60, 120, 240 and 480. So this is going to be loading. Then we are going to unload to 120 kPa and then reload to 240, 480, 1000 and 2000 kPa. So imagine that we have a soil specimen, cylindrical soil specimen. It's going to be about 2.5 inches in diameter and 1 inch in thickness, okay, which can only settle in the vertical direction. So this is HTI, initial sample height. Okay. And then this is going to have just solids, which is height of solids, and this is going to be height of voids, and this is going to be mass of solids, which is not going to change because the total amount of soil is always going to be the same. So the only thing that going to change with applied load is that the void space is going to become smaller and smaller. Okay, so we are going to make use of this, and we are going to do the whole test, and at the end of the test we are going to determine dry mass of soil specimen at the end of the test, MS, because that's going to be the same at the beginning of the test and we cannot disturb our samples. So the best thing to do is measure it at the end of the test. And we know that mass of soil is going to be equal to specific unit weight of the soil particles times the volume of solids, which is specific gravity times density of water times height of solids times the cross-sectional area of the soil, which is the volume of solids, and that will give us HS, MS, A, GS, rho W. We are going to assume this to be 2.7 for our soil. This is the cross-sectional area of the soil. and your data sheet contains the diameter of the specimen, so you can calculate that. We know the density of water, and this mass of solids is given to you in your data sheets. So once we know this, referring back to this diagram, we can figure out that height of voids is initial height minus height of solids, and that will give us information on initial void ratio E0, which is this value of height of voids in the beginning divided by the height of solids. And this is an important number you need to do the calculations. So once again, let's quickly look at, so we have a clay specimen sandwiched between porous stones, so the water can squeeze out of it, of the clay specimen. Its initial height is going to be HTI, the entire specimen, and it is going to have certain amount of voids and height of solids, and height of solids won't change throughout the test. So this is our initial condition. Okay, then on this specimen we are going to apply a load that's equivalent to 15 kPa. Okay, and in reaction to that, it's going to settle by an amount delta H1. Okay, so its initial height was HTI. So initially it was HTI, and then it settled to by delta H1. So the change in void ratio, so we already saw how much was the initial void ratio and how to calculate that before we started applying any stresses. So the change in void ratio is going to be delta H1 divided by HS. So the new void ratio E1 is going to be E0 minus delta E1. Okay, then we are going to increase the load or the stress to 30 kPa, which is going to have a total change in height as delta H2. So delta E2 is going to be delta H2 divided by the height of solids. So E2 can be calculated as E0 minus delta E2. Okay, so we do that for all load increments, and we get a relationship between sigma, which is the applied stress, and void ratio. Okay, so this is applied stress and versus void ratio. So we have loading sequence of 15, 30, 60, 120, 240 and 480 kPa. Then we unload and then reload again. So during each of the load increment, we keep track of change in sample height, as a function of time. And we are going to use that information to find the coefficient of consolidation. But in this particular table down below, for each normal stress, we have the settlement that took place at the end of the loading. So what happens that once you apply 15 kPa, you start making recordings, at 15 seconds, 30 seconds, 1 minute, 2 minute, all the way to 24 hours. That's how a consolidation test used to be done. So if you had like 10 loading stages, as we are doing here, the test will go on for 10 days. But now with automated process, the program itself keep track of change in settlement. And if the settlement is not appreciably changing, then it automatically goes on to the next loading stage. Um, and when that happens, we record the final settlement before the loading is changed. So this particular table we are seeing here gives us the loading, the settlement at the end of each loading stage. So using this information, we calculate the specimen height at the end of the load increment. The height of solids is not changing. We find the height of voids and keep track of the void ratio. So for each load increment, at the end of it, we'll have a new void ratio. So we plot that void ratio versus the normal stress. So here I have an example. The normal stress is in PSI. In your test, those are in KPA, but here I'm picking an example where they are in PSI, and the void ratio is on y-axis. So the data point will look like these. So we use by hand or by computer, we can draw a curve passing through that. So this is 15, 30, 60 kPa and so on. Here it's in PSI. Then we unload, reload, and then we start loading again. Okay. So loading, unloading is done so that we can obtain recompression index, which is essentially that curve is parallel to this part. But sometimes at low stresses in the test, we don't get good data in that range, and that's why loading, unloading here is useful. And then this passes the pre-consolidation stress at some point, and this is called virgin compression curve. Which is after the pre-consolidation stress is passed. So we are going to use this data to find compression index and recompression index. So both compression index and recompression index have the same equation, which is essentially change in void ratio divided by change in log sigma, which are the slopes of these lines. So for C sub C compression index, we want a slope of this C sub C, and for recompression index, which sometimes is called swelling index, we want a slope of that, which is called C sub R. Then I have replotted the data here in order to show how the pre-consolidation stress could be determined. So pre-consolidation stress sigma prime C is, or sometimes it's referred to as sigma prime P, is the stress the soil specimen has experienced when it was in the ground in the past, the maximum stress it has experienced in the past. So imagine that if we have soil layer that's settled under its own weight, the pre-consolidation stress is going to be the overburden stress at that depth where the sample came from. But there could have been an iceberg sitting at that location thousands of years ago. In that case, it has seen higher stresses in the past than the current stresses. Or there could have been a multi-story building that's now removed, and that's another example where there could be high pre-consolidation stress. So if the soil has been subjected to pre-consolidation stress, we see that initial slope changes, and then it passes the pre-consolidation stress and it becomes steeper. So in order to find the pre-consolidation stress, it is important to find a point of maximum curvature. So in this case, it is a point of maximum curvature, or if you attempt to draw a circle at this point where this part being tangent, you can draw the smallest circle at that location. So I'm going to pick this point as the point of maximum curvature and draw a horizontal. And then we are going to draw a tangent, and then draw a bisector such that this angle is same as that angle. And then we are going to take this part of the curve, which is the compression curve, and extend it backwards, and wherever that intersects, we are going to find that stress to be the pre-consolidation stress. So in this case, it is going to be 20, 30, 40 psi is going to be the pre-consolidation stress. Okay, so you will be doing this kind of a construction, originally suggested by a researcher called Casagrande, and you will find a pre-consolidation stress, compression index, and this slope as a recompression index. So these three properties will come out of the data so far. Then we move on to coefficient of consolidation, which uses the equation TV, which is can be found from a table, time factor times the coefficient of consolidation CV, time divided by the sample height square. And this actually oftentimes has a subscript dr, which is distance of drainage path. So if we have our specimen, okay, of a certain thickness, you know that it can't expand in the horizontal direction, and only way it can change its height is in the vertical direction. The height of drainage path is half the specimen height. Because we have porous stones on both sides, the maximum drainage path that a soil water particle is going to have here in the middle is either going up or going down, and it's half the thickness. So that's one thing to remember. And we are going to use two methods. One is called square root of time method, and another one is logarithm of time method. So here is an example. So in your data sheet, I took the data from 1000 kPa. So this is what I was talking about. As soon as the load of 1000 kPa or the stress of 1000 kPa was applied, you start making measurements at 0 minutes, 0.1 minutes, 0.25 minutes, 0.5 minutes, and so on. And in this particular case, the program went on to the next loading increment of 2000 kPa after 25 minutes. Okay. So you use the displacement and find sample height So you will have that column here, and then square root of time. So essentially 4 is becomes 2, square root of 4 minutes is 2, 16 is 4, and so on. 25 will be 5, right? Okay. So you have that axis, square root of time, which is presented on the x-axis. So this is square root of time, and specimen height is on the y-axis. So again, we draw a curve through the data points. Okay. And the way to do it is we extend the initial straight line portion to the back, and wherever that intersects, we draw a line that has a slope of 1.15 times the slope of this line. Okay. So the way to do it is, maybe the easiest thing is to extend it all the way to the bottom. Measure this physical distance. Let's say it is 3 centimeters. Then you draw a point that's 1.15 times 3, which is 3.45. Obviously, I didn't draw this well, so I'm going to delete this and say 3. So this one, okay, if I extend it to be precise, it looks, if I measure this physical distance, it's, let's say, this physical distance is 3 centimeters. So 1.15 times 3 becomes 3.45. So I measure that, which comes out here, let's say, and we draw this line to this point again. And wherever that intersects the curve, that number, in this particular case, it's about 2.8, and that corresponds to 90% consolidation. Okay, so T90 square root of that comes out to be, in this particular example, 2.8. So T90 will be 7.84 minutes. Okay, and then we use the equation, which is TV is equal to CV T90 divided by H square, HDR. So TV for 90% consolidation is 0.848. CV we want to find out. T90 in this case is 7.84 minutes. And then HDR is the average sample height. Okay. So this is average sample height. So you have the first number here and the last number here, and you find that as an and you find the average of the two. That gives you average sample height, and HDR will be divided by 2, and that gives you HDR. Okay, so average sample height divided by 2. Okay, and that's how you find CV. And I'm asking that you report it in meter square per year. So you have to change all your dimensions of the units at the end and convert it into meter square per year, so you can compare it with typical values. Finally, the second method to use is square root of time method. So again, you have time elapsed in minute and displacement. using displacement, you calculate specimen height or sample height in millimeters. And again, I'm using 1000 kPa data. So for this, the sample height is plotted in millimeters on the y-axis, and you calculate the logarithm of time in minutes. So you convert the time elapsed and take a logarithm of that. So we are going to join these points. Okay. Then we are going to pick up any time in the initial flat portion, okay, T1, and multiplied by 4 times and tie 4 T1. So if this was 0.2, this will be 0.8. So we take that up here, and whatever this vertical distance is, we add that much on top. And that gives us our initial reading at 0. So once we determine what this point is, I lost my curve. We take this straight line portion and extend it back. We take this straight line portion at the end and extend it back. And that comes out to be, we call it 100% consolidation. And then we find midpoint of this point and that point somewhere here, looks like. And we find this. So you read it on your log scale and looks like this is about 2.6. Okay, so our T50 for 50% consolidation is going to be 2.6 minutes. Okay, so again the equation will be, we want to find CV. T50 in this case is going to be 2.6 minutes. HDR, we calculate it again as the average sample height divided by 2, and TV for 50% consolidation, it's 0.197, and that's how you calculate CV. Once again, report it in meters square per year.